Let's go back and reconsider our system that we had from the day before. Remember, we had this system here where we had mercury, and it was in a 1 molar proton solution. How are we doing here? Okay. So in other words, we have a mercury electrode, and we're putting that in a 1 molar solution, and then we'll have a reference electrode versus that. And we know that, let's suppose it's 1 molar hydrogen ions and 1 molar chloride ions. Now, if we do a potential voltage curve, again, current is on the y-axis and potential would be on this axis, we could draw and say that over a range of potentials, no reaction would occur. In fact, only until we get quite negative do we get a reaction for the reduction of hydrogen ions to hydrogen gas. But quite quickly, as we go to positive potentials, we see a reaction to form Hg2Cl2, which is a calomel type reaction. On the other hand, if we take that same system, and we'll draw it in red here, and we have, instead of a mercury electrode, we have a platinum electrode in 1 molar H plus and 1 molar chloride, we get quite a different looking curve. In fact, as we approach the zero on this scale, the reaction quickly occurs. In other words, on a platinum electrode, we see a reaction to hydrogen gas. And on the oxidation side, in fact, what we see is not the formation of mercury chloride, but we see the formation of chlorine gas from chlorine. Okay, so this shows you the fact that, in fact, we have different electrodes, we can have different types of chemical reactions occurring, and the difference between these two basically is a kinetic difference. In other words, this reaction occurs very slowly on the mercury electrode, the proton reduction, but it occurs quite rapidly on the platinum electrode. In fact, there's about a 9 order of magnitude difference in the reaction rate on those two systems. Okay. Now, if we take this system, we find that it turns out we have to be at about minus 1.8 volts to get that reaction to occur. And we call this system kinetically polarized. Remember, we use the term polarized to indicate a system where the electrode has acquired a potential. In this case, we're polarizing the electrode by applying some external potential to it, but it's polarized because it's allowed to be put at that potential without any significant current being flowing. In this case, the platinum electrode cannot be kinetically polarized in this system at a very negative potential because the reaction occurs rapidly. On the other hand, we can think of systems that are what we call thermodynamically polarized. And for example, on a platinum electrode, remember we talked about anthracene and acetonitrile. And a platinum electrode with anthracene in it and acetonitrile, we saw that it had a reaction current potential curve something like this, where we required negative potentials to form the radical anion, and we required positive potentials to form the radical cation systems. In other words, we had to apply potentials to do a electrochemical process. In this case, the electrode is polarized again, but it's polarized by thermodynamic considerations. So it would be thermodynamically thermodynamically polarized. In other words, the reaction is not limited by kinetics, but it's limited by the fact that until we get sufficiently negative or positive, the reaction is not thermodynamically predicted to occur. And so there's not any energy for it. So this is an important aspect of electrochemistry, is to sometimes we'll have systems that are not occurring because there's a kinetic limitation, and sometimes we'll have systems that are not occurring because we have a thermodynamic limitation. The important thing to remember is that even though this reaction, for example, the mercury, the reduction of protons on mercury is assumed to occur, or thermodynamically should occur at a very low negative potentials, in fact, kinetically it's slow. Now remember what we called this current that was flowing out at these points. We called this a Faradaic current. We call it Faradaic because it's in honor of the guy Michael Faraday, who first showed that the amount of current that's flowing is directly related to the amount of chemical reaction that's occurring. So you would expect that if I took a potential and started, say, from this potential and stepped out to here, or if I stepped the potential from here, or any point in between this point where the current actually starts to flow, we should see no current flowing. And in fact, that's true. If we put the potential at any of these points and we wait a long time, we see that no current flows, or very tiny amounts of current will flow under those situations. However, there is a dynamic effect that happens. Remember, we're asking, let's suppose we take this system up here again. I can't put both of them on the same, but this is this reaction of protons on a mercury electrode. And I do a system where I dynamically step the potential of the mercury electrode from 0 to -1 volt. Okay. Now again, if I step to -1 volt here, there should be no current flowing. But in fact, we see this sort of situation. If we assume that's time equal to 0, we get a curve that looks like this. Initially, we see 0 current because we haven't done anything yet, but at the point where we do the step at time equal to 0, we get a very large increase in current and then a decrease in the amount of current with time. So what's happening here? In this dynamic experiment, we predict that no Faradaic current will flow, so the current that's flowing must be a non-Faradaic current. In fact, that's what's happening. This is a non-Faradaic. If we look at that carefully, we can do a couple things. First of all, we can integrate that current and get the amount of charge that flows during that system. And notice that it goes to 0. In fact, it goes in sort of an asymptotic approach to 0. But after a reasonable amount of time, it's effectively equal to 0. So we can integrate over that time frame and get the amount of charge that has passed in that particular case. Also, if we look at that system, we see that the curve looks a lot like an exponential decay. In other words, it has the characteristic of an exponential, mathematically exponential function. And in fact, this looks exactly like the current you'd see at a capacitor. If we take a capacitor, and remember, a capacitor is a device that they use in electronics to store charge on metal plates or conducting plates. And if we step the potential on a capacitor, we get these sorts of exponential curves. So our electrode, the mercury electrode in the 1 molar HCl solution, acts like a capacitor when we step the potential. All right. So the current we're seeing here again is not due to a chemical process that's occurring. It's occurring due to some sort of a capacitor type process. Now let's do some electronics here just for a minute. Suppose we have a system, an electronic system composed of a battery and a capacitor, okay, and a switch. Here's our switch. Here's our contact on the switch. Here's the battery. That's the symbol for a battery, those alternate short and long lines. That's capacitor. Now the capacitor is initially uncharged, but what happens when we close the switch? Current will flow, okay, on a capacitor. In fact, what we see is that current will flow so that we get electrons moving in this direction, and we get a charge build up on the plates of our capacitor. And so we get a separation of charge on that capacitor. Now, charge does not pass through the capacitor, but we do get an amount of charge flows. And now the charge will flow until the voltage on the capacitor equals the voltage on the battery. How much charge flows? Well, the charge would be given the abbreviation Q. And for a capacitor, the charge is equal to the capacity times the voltage, or the capacitance, I should say. And that's in coulombs. And then that would be the volts, the voltage. So whatever the battery voltage is and whatever the capacitance is would be how much charge would flow in that particular system. And we can either calculate it from the capacitance and the voltage, or if we didn't know, for example, what the capacitance was, we could integrate the current that flows from 0 to infinity and get the charge of the system that way. And that would give us that particular system. Another thing about capacitance is that we can now characterize the capacitance of a particular type of capacitor as this, where the capacitance is equal to what they're called dielectric constants, and this is this is called the permittivity of free space. Okay, and that would be essentially the vacuum dielectric constant in real units. And the dielectric constant here, shown by epsilon, capital epsilon, is a normalized quantity. For vacuum, E is equal to 1. E is approximately equal to 1 in air. E is 77 for distilled water. And E is about 6, approximately 6 for things like glass. Plastics might have a dielectric constant of 3 or so. So what's that mean? Well, that means that if we compare back up to this system, we see that for a particular type of capacitor, and this would be in fact a parallel plate capacitor, the dielectric, the amount of capacitance that we have depends on the dielectric constant and this term here, which is the distance between the plates. So having a higher dielectric constant means that we're going to have a higher capacitance, all things being equal, keeping the same distance. So if we compare a capacitor made with vacuum between the plates to a capacitor made with distilled water between the plates, the capacitance would be about 77 times larger. So since our electrochemical cell is made out of water mostly, we expect actually a large capacitor effect because of that. Now let's take our system again and put our mercury electrode in contact with, let's change it a little bit. Let's make it some sodium ions and chloride ions in solution. And we'll put on the other electrode just as something to be in the other system. Let's make it platinum. If we apply a potential across this system, this sodium chloride system, for the mercury and platinum, in fact, there will be a range of potentials where no Faradaic current can flow, but we'll get this capacitive type process occurring. Now, how does that work out? Well, because our mercury electrode has got a negative potential to it, there's going to be a buildup of charge on that mercury electrode. Why is there a buildup of charge? Because there is no Faradaic reaction that can remove that charge from it. Whenever we have this electrode polarized, we have some charge on that system. Likewise, the platinum electrode will have a buildup of positive charge as well on the platinum electrodes. Now the solution, because those ions are in solution, they're mobile, they can actually become attracted to that negative charge. And so we can take our sodium ions and have them be attracted to that electrode. And we can have the chloride ions being attracted to that electrode. They're attracted, they're being close to that electrode, but they're not having a reaction. They're not having a Faradaic reaction because there is not enough energy, for example, to take an electron from the mercury metal and put it onto that sodium ion. That requires more energy than is available in this particular system. But those sodium ions and chloride ions are not completely separate. In fact, there's chloride ions around. They're just not as close to the electrode as they are as the other ones are. So what's happening here? Now we see the agreement between our physical system, the electrode in a solution, and the capacitor. In the capacitor we had parallel plates of metal. Here we have a plate of metal and a region of solution. But the distinguishing features are very similar. We have a buildup of charge on one side of that metal and a buildup of charge on the solution phase. And so this separated charge region is just like a capacitor. So as we apply different potentials to the system, we expect capacitive behavior out of our electrode in solution, and that's exactly what we do see. Because these ions are very small, the distance is quite tiny. And so not only do we have a large dielectric for water, the electric constant for water, we have a very tiny distance. So that means that the capacitance of our electrode is not inconsiderable. It's actually quite large, and a fact that's been used actually to make capacitors that you use for electronic devices as well. So it's not something we can ignore. In fact, we always have to worry about this, what they call double layer charging in the system. All right, so let's do an experiment on our head. Let's take a system like this, where we have a cell, electrochemical cell, that's separated again by a porous plug. And on one side of that cell we have a solution that's containing a platinum electrode. There's our platinum electrode. It's encased in glass at every point except for the end, so maybe it's a little disc-shaped electrode. And what about the other one? Let's make it a pool of mercury and in a sodium chloride solution. So essentially it's like a saturated calomel electrode, and we'll make a little connector there for that as well. So we have mercury metal in solution with in a chloride solution, and then we have our platinum electrode, and also let's suppose it's in a sodium chloride solution with a little porous frit. So here what we'd have mercury, a cell would be, well, I said sodium, not potassium, so let's make it sodium. We'll have our porous frit, and then on the other side of that system, basically we have, the only thing that's really important is that we have this mercury chloride called calomel and mercury in solution. And remember, we're going to use this kind of as a reference electrode. And so this is the SCE reference electrode, or the saturated calomel electrode. We haven't talked about that too much, but we'll talk about it later, so just keep that in mind. Now, since these system is set up, we don't really have any opportunity for Faradaic reactions to occur. We know that the sodium ion is not going to react with the platinum electrode electrochemically, except at very high potentials, and we're going to ignore those. And so we have now, instead of a chemical system or an electrochemical system to worry about, we have basically a purely electrical system to think about. And in fact, what we can do is we can make a model electrical circuit out of our cell. And we can draw a capacitor, a resistor, and we'll call that resistor R sub solution, and we'll call this capacitor C sub Hg. Oh. I said that was platinum, didn't I? But let's just have it. That's just mercury. So sorry about that. And then we have another capacitor. We'll call that SCE. And again, we'll have a circuit with a ammeter, or a current meter in the system, a switch, and a potential source. And we'll have a variable potential source, so we'll use a little arrow there to indicate that. So here's our electrical circuit. Now, if we close that switch, what's going to happen? Well, those capacitors are going to start charging up, just like we predict as before. The resistance of the solution, though, will limit the rate of that reaction, because it's the larger the resistance, the slower the current can actually flow through that system to balance the charges out. Well, it turns out also that if we make some simplifying assumptions, let's suppose the resistance of the solution is very small, then essentially we have a system like this, where we have two capacitors in parallel. And if you remember from physics, if we calculate what the effect of two capacitors in parallel is, the total capacitance is equal to 1 over C1 plus 1 over C2, and C total is then equal to C1, C2 over C1 plus C2. And so my point is that if C1 is much, much greater than C2, Ct is approximately equal to C1. Because what will happen if C1 is much, much less, then this effectively becomes 0, and that cancels out. And so Ct is approximately equal to C sub 1. So it's kind of a non-intuitive effect, but in fact that's the way it works out. The largest capacitance in the system becomes minimal. We don't have to worry about it, and the effective capacitance of the system is driven by the smallest capacity. Now, usually the way we have our system set up, we have our electrode of interest, which maybe is this one over here, much smaller than our reference electrode. The reference electrode is designed to have a large surface area and so on. So it has usually the largest capacitance. So usually we can rewrite our cell without too much worries of being incorrect as like this, and ignore entirely the effect of the reference electrode in the system. Okay, I screwed that up, but there's a battery, and so on. Okay, so again, at that point, our relationship between the model electrical circuit and the reality is, again, we have a mercury electrode with a buildup of negative charge on the one side and perhaps a positive charge on the other side. So these are ions absorbed at the electrode surface, either absorbed or very close to the electrode surface. So you have this nice capacitive process. Now, capacitance of this electrode is called the double layer capacitance. Why is it called that? Well, you can see there's a double layer. There's a layer of charge on one side of the electrode, and there's another layer of charge on the other side of the electrode. So this charge is a double layer. And so electrochemists are always talking about the double layer capacitance of their electrode. And so we abbreviate that by C sub D. And that is typically equal to 10 to 40 microfarads per square centimeter. So it depends, obviously depends on the size of the electrode. If larger the electrode, the more area we've got, the more capacitance that we're going to have. So this in fact is a what they call a specific capacitance, because we've used the area in the term. Okay. So there's two things to think about here. Now we've got a charge on the electrode surface that we can vary by varying the potential of the electrode. Even if we don't allow any chemical reaction or Faradaic reaction to occur, we can move ions around from the solution to be attracted or repelled by the metal electrode, because we can change the potential of the metal. And so actually we use a specific term for that. The potential of the metal is phi sub m. When we talk about metal, that's usually metal electrode. Now, in fact, we could have carbon electrodes, which aren't metals, but so usually we'll use phi sub m even so. And phi sub s is the potential of the solution. Now, the potential difference between the metal and the solution has to be 0 in this particular case, because we have to have electroneutrality for the system. We're putting in so many electrons from our power supply, but that electron charge, for example, on the metal has to be balanced out by an equal potential on the solution. So because of the electrostatics, we have to have the metal potential equal to the solution potential at that electrode surface. Now, we don't necessarily have to have a potential on the metal. Whenever we have a buildup of charge on the electrode surface like that, we're going to have a potential in the system, because that's really what a potential is. It's an excess amount of charge in the system. But we can actually have systems where the phi sub m is equal to 0. And in that case, they call that point the potential of 0 charge, and we'll come across this later, but we'll refer to it now as the potential of 0 charge, or the PZC. Now this is not the same, PZC is not the same as having an applied potential of 0, because just because we have an applied potential of 0 does not mean that we don't have an excess amount of charge on the electrode surface. We can have an excess amount of electrode charge depending on whether we have, depending on the system properties, or the solution properties, and so on. Remember, that potential of 0 is an arbitrary construct that we've assigned to it. It doesn't actually have to do with the real potential of the interface. So it's possible to have charge on the metal surface even if we have an applied potential of 0 to it. All right. So now let's take a look again at our electrode model. So we can make it very simple now. We have C sub D and R sub S, or R sub solution. And you might remember this if you took physics in college, and you probably all have. You can actually derive the electrical properties of this capacitance solution, or capacitor resistor circuit. So if we take this circuit and we do a step of the potential from time equal to 0, from say some initial potential to some final potential E0, EF. We would observe a current with time behavior very similar to this. And that, again, is an exponential function. Now, you can derive that. You might go back and look at that derivation, but you'd see that in that case that the current that flows is equal to E sub f over R sub s times the exponential function of minus t over Rs CD. And if we take the natural log of that current versus time, we see that there is a straight line behavior, and we can see that the natural log of I is going to be the natural log of E sub f over Rs minus t over Rs CD. So the slope of that would be minus 1 over Rs CD, and the y-intercept would be natural log of E sub I over Rs CD. So why am I talking about this? Well, because this is, like I said, a very important aspect of the electrochemical system. By understanding our simple model cells, we can actually get more information about our actual electrode behavior. For example, by knowing the capacitance of our electrode often gives us information about the actual area of our electrode. And by looking at the charging-discharging curves of the electrode solution capacitance, we can get information about the solution resistance, something that we may not know directly. Okay. So whenever we do a step like that, we expect this exponential charging current to flow. Now, another common type of electrochemical experiment is, instead of a step, we do a potential sweep, where we take versus time and potential, we apply, for example, some initial potential and then sweep at a constant linear rate with time, and then perhaps we sweep back with time. So T getting larger. What would be the current that would flow under these conditions? Again, we're assuming no Faradaic reaction, no chemical reaction, just the charging and discharging of our double layer capacitance. Well, that's a little bit more difficult to derive. In fact, you can do it. Because we've got that initial step there, we actually get kind of two behaviors. We get a behavior like this, where we do a step, and we also get a behavior that's related to the sweep. And it turns out that we get, first of all, a term that's VCD. Space there, but that's T over Rs C sub D. So you get an exponential term here as well. And so essentially what you would see for the current would be something like this, or the current versus time. You would see an initial kind of this step type curve, and then it would level off with at long time to be equal to VCD. V is actually the slope of the system. So V is equal to the sweep rate. And for example, that might be in terms of volts per second. So it's essentially the slope of that particular curve. The important thing to note is that with a constant sweep rate, a linear sweep of the potential, we get a constant charging current. In other words, we get a kind of this flat charging current that doesn't vary with time after we do this initial process. Now, in fact, I've drawn that a little bit incorrectly. Let me draw this again, because what happens when we change the slope of our sweep? And let's change it so that instead of starting out at some initial potential, we'll start at 0. That makes it a little bit easier. So here's our E. What happens to our T? Well, right at this potential, notice that the slope of our potential change has shifted to be negative. So again, T. So our current would start out, and it would have a constant value of V. Sorry about that. VCD, and then as we change the potential slope, or the sweep slope, we get a negative V sub, signal. So here again is our current versus time. Perhaps I should have used a different color pen. Yeah, to indicate that particular case. Now, as I said, this is a very common experiment, and in fact, when we apply potentials like this, they call this cyclic voltammetry, or variations of that term. And it turns out that an interesting way to plot that is to not plot the current versus time, but to plot the current versus the applied potential. And when we do that, we get a curve that looks like this, where this is current here, but we're applying a potential, so we get a current, sorry about that, current potential curve. And depending on the applied potential, we would get curves that look like that. And so you see the current folds over because of the way we've started out. We've got this initial positive slope and then a negative slope, so we're going the potential out and then back, and we've plotted our signal this way. And if we double the slope, if we sweep twice as fast, the current would be twice as large. What's the effect of that? Again, as we go to shorter time scales, the charging current becomes larger, and the shorter time scales implies faster sweep rates, and the charging current becomes larger as well. Okay. Well, we'll see. In fact, the discussion paper shows you very graphically this effect as we go on. And